One of the uses for the integrated rate law is to calculate the half-life of a compound. The half-life is the time required for the concentration of a reactant to decrease to 1/2 of its initial value. So, for example, if you have 100 grams, the half-life is the amount of time it takes for it to decompose to 50 grams. Well, there are multiple ways of determining the half-life of a compound. The most efficient is to use the integrated rate law because it incorporates an opportunity to include both an initial concentration as well as the concentration that would exist at the half-life. Okay. If you know the K constant, this allows you to calculate the T, the time required to accomplish this decrease in concentration. For a first-order integrated rate law, solving for T looks like this. You begin with the integrated rate law. Okay. And in order to isolate the time, you need to move the natural log of the initial concentration over to the left-hand side, like this. Okay. Then, because by definition, the ratio right here between those two concentrations is going to equal 1/2, you can input that half into those parentheses. Okay. Solving this gets you to the natural log of 2 equals kT. And the natural log of 2 is always going to equal 0.693. The most important thing about this simplification of the integrated rate law is that it shows why half-life is most useful for a first-order process. For a first-order process, the half-life is the same for any initial concentration. Once the equation is simplified, the concentration is removed, and the half-life depends solely on the K. So if you start with 100 grams and decompose it to 50 grams, it will take the exact same amount of time as decomposing 1,000 grams to 500. For a second-order reaction, as well as for a zero-order reaction, the simplified versions of their respective integrated rate laws do not function in the same way. In both cases, the initial concentrations are still incorporated into the half-life equation. This means that the half-life does depend on the initial concentrations for these orders. One application of this concept has to do with radioactive isotopes. They have a variety of uses as well as a large amount of dangerous consequences for humans. For example, radioactive radon-222 is a gas that comes from natural sources. It has a half-life of 3.8 days. Okay. And as a result, because it comes from those natural sources, it has a tendency to build up in basements. Okay. So if we begin with a sample of 4.0 times 10 to the 13th atoms of radon-222 per liter of air, how many atoms of radon-222 per liter will remain after 1 month? Okay. To begin, we need to calculate the half-life of this reaction. We already know the number of atoms at the beginning, and we already know the elapsed time. Okay. So what we need to do is take our K, which we don't yet know, set it equal to the 0.693, and divide it by the half-life of 3.8 days that we were given in the problem. Okay. This allows us to determine that our K value is 0.18. Once we have this value, we can plug it into our integrated rate law to get that the natural log of the concentration of radon after the half-life has passed, compared with our initial concentration, okay, is going to equal the negative K value that we just determined times the number of days in question. Okay. This is going to give us, this number right here is going to give us negative 5.5. And so if we try to solve out the natural log from this equation, we're going to wind up with the concentration of the radon after time t over that initial concentration times 10 to the 13th is going to equal e to the negative 5.5. Solving for this will allow us to find that this initial concentration should equal 1.7 times 10 to the 11th, the units being atoms per liter. Now go ahead and try, actually let's go back real quick. Now go ahead and try exercise 15.9 on page 692. I'll write that down.